Welcome to this video on 1D transient thermal modeling, prepared by Dr. Qureshi from the National University of Singapore. He specializes in the area of computational modeling and simulation to solve complex energy challenges. We begin with Part 1, covering the fundamentals of heat transfer and thermodynamics in the subsea environment. Deepwater operations face a significant thermal challenge. Reservoir fluids start hot, but lose heat rapidly to the cold 4-degree seawater. This can lead to solid deposition, like waxes or hydrates, causing costly pipeline blockages. Poor thermal design is extremely expensive. Remediation of a single hydrate plug incident can easily exceed $10 million in lost production and specialized intervention costs. Heat transfers through three main mechanisms: convection between fluids and pipe walls, conduction through the pipe layers, and radiation, which is generally negligible in this environment. The overall heat transfer coefficient, or U value, quantifies heat loss through the composite pipe barrier. A lower U value indicates better insulation, as shown by the governing equation. This table highlights typical U values for various configurations, ranging from bare steel pipe to high-performance pipe-in-pipe systems used in deep-water tiebacks. Environmental boundaries matter. A pipeline in open water experiences high convection from currents, while one buried in seabed soil benefits from the natural insulating properties of the sediment. Next, in Part 2, we examine the insulation systems that act as physical barriers to heat loss. Common insulation technologies include wet insulation using syntactic foams, pipe-in-pipe systems for high-performance needs, and the use of burial or trenching. Syntactic foams are cost-effective for moderate depths but can degrade over time due to water ingress or crushing, which increases the thermal U value. For ultra-deep water, pipe-in-pipe systems are the ultimate thermal barrier, protecting dry insulators within a sealed annulus, though they come with higher costs and installation complexity. During steady-state flow, fluid temperature decays exponentially. Designs must ensure the arrival temperature stays above the critical hydrate or wax formation temperatures. Finally, Part 3 introduces transient thermal modeling to simulate the dynamics of time. Steady-state models are not enough. Transient modeling is essential for evaluating shut-in operations, helping engineers predict how fast the stationary fluid will cool towards seabed temperatures. To predict temperature profiles over time, we use the 1D transient heat conduction equation. It is a parabolic partial differential equation relating the rate of temperature change at a radial point to the spatial curvature of the temperature profile. Finite difference numerical methods are used to solve this equation. The explicit method is simple but requires small time steps for stability, while the implicit method is unconditionally stable but computationally more intensive. Numerical instability is a critical danger. If you violate the Fourier stability criterion in an explicit scheme, your temperature values can explode to infinity in just seconds of simulated time. To build a model, you must discretize the pipeline into nodes. We define spatial and time steps, set initial temperatures from steady-state data, and specify boundary conditions for heat from the fluid and the cold seawater. The Fourier number governs stability. If you increase spatial resolution by halving the radial step, the time step must be divided by 4. Commercial software typically defaults to implicit solvers to avoid these constraints. Moving to Part 4, we will discuss cool-down time estimation, a crucial race against time for subsea operators. A shut-in occurs when production stops. The main objective of transient thermal modeling here is to generate a cool-down curve, showing the bulk fluid temperature drop over time since the shut-in. As shown in this cool-down curve, the fluid temperature decays toward ambient seabed levels. The operational window is determined by how long it takes the fluid to reach the hydrate formation temperature. The no-touch time represents the critical window operators have to assess a shutdown and attempt a restart. If this time expires, serious intervention like depressurization or displacement must begin immediately. If the fluid enters the hydrate stability zone, operators can use depressurization or displacement to clear the line. Displacement involves pumping dead oil or methanol to push hydrate-prone fluids out of the cold section. Part 5 explores advanced thermal management through active heating, which provides greater control over pipeline temperatures. Active heating technologies include direct electrical heating, electrically trace-heated pipe-in-pipe systems, and circulating hot fluids to maintain temperatures during prolonged shut-ins. The thermal design lifecycle progresses from conceptual target setting to detailed design refinements, and finally to operational procedures for handling unplanned shut-ins within the allotted time. To summarize, transients drive design, U-value calculations are vital, implicit solvers ensure stability, and active heating is becoming the preferred choice over excessive passive insulation in deep water. Thank you for watching this module on transient thermal modeling. Please let me know if you have any questions before we move to Module 9. If you are interested in consulting, research collaborations, or technical training, please feel free to reach out via the email addresses provided or connect through my professional network.